In this video, we're going to be looking at rotational kinematics, specifically situations with uniform angular acceleration. We'll start by discussing the conditions needed for uniform angular acceleration. Then we'll define the key variables. After that, we'll look at the equations we can use when alpha is constant and see how they link to the linear Suvat equations you already know. We'll then go through a few worked examples to see how to apply these ideas. Then we'll take a look at the key features of the graphs of angular quantities against time. And then finally, we'll finish with one last example that involves interpreting a graph. So let's start by thinking about what it actually means for an object to have uniform angular acceleration. Uniform angular acceleration happens when there's a constant net torque acting on an object. So the total turning effect of all forces must stay the same over time. Remember, torque depends on three things: the force, the distance between the pivot and the point of action of the force, and the angle between F and R. So for the torque to stay constant, F, R and theta must all remain constant. For example, consider a rod hinged at one end. If the force remains the same size and always stays at the same distance and angle from the pivot as the rod rotates, then the torque stays constant, so the angular acceleration remains constant as well. But if any of these change while the rod rotates, the angular acceleration will no longer be constant. For instance, if the force always stays vertical, then theta changes as the rod rotates, so the torque and therefore the angular acceleration will also change. Now let's take a look at the three main quantities that we use to describe rotational motion. The first one is angular displacement, theta. This is simply the angle through which the object has rotated about its pivot. If we imagine this yellow rod rotating, the angular displacement is the change in angle from its starting position to where it ends up. We can see that first in the animation with the pivot at the centre, and then again with the pivot at its end. In linear motion, the equivalent quantity is displacement, which we call S. The two are related by the equation S equals theta r, where r is the distance from the axis of rotation. So the further from the pivot you are, the larger the linear distance moved for the same angle. The second quantity is angular velocity omega. This is the rate of change of angular displacement. Its linear equivalent is velocity, and the relationship between them is v equals omega r. Again, the same angular speed gives a larger linear speed for points further from the axis. Finally, we have angular acceleration alpha. This is the rate of change of angular velocity. Its linear equivalent is acceleration a, and the relationship between them is a equals alpha r. Just like linear acceleration, a negative value of alpha represents slowing down, i.e. decreasing angular velocity. So in summary, theta, omega and alpha are the rotational versions of s, v and a, and each one links to its linear counterpart through the radius r. Now let's look at the equations of uniform angular acceleration. They are analogous to the equations of uniform linear motion that you've probably seen before. Both sets describe motion where acceleration is constant, but one applies to objects moving in a straight line and the other to objects rotating about an axis. For linear motion, we use displacement s, initial velocity u, final velocity v, acceleration a and time t. For rotational motion, these have direct counterparts: angular displacement delta theta, initial angular velocity omega I, final angular velocity omega f, angular acceleration alpha, and the same time t. Each linear equation has an angular version that looks almost identical. Substituting the analogous angular variables into the equation v equals u plus at, we get omega f equals omega I plus alpha t. We can then do a similar substitution to the other four equations to get the equations of uniform angular acceleration. These last equations aren't in the IB data booklet, so it's useful to either memorize them or learn how to derive them. Now let's go through a couple of calculation examples. The goal is to identify what's given, choose the right equation, and then substitute carefully. In this example, we have a rod that starts from rest and experiences a constant angular acceleration. We're asked to find the angular displacement after 3 seconds. Step 1 is to identify the known quantities. The initial angular velocity here is 0 because the rod starts from rest. The angular acceleration is 0.50 radians per second squared, and the time is 3 seconds. Next, we choose an equation that contains what we know and what we want. We're trying to find angular displacement, so the most suitable equation is delta theta equals omega it plus a half alpha t squared. Now we substitute everything into the equation, checking that our units are consistent. Everything is already in radians and seconds here, which will give us the desired unit of radians for angular displacement. The first term disappears because the initial angular velocity is 0, so delta theta equals 1/2 times 0.5 times 3 squared. This gives about 2.25 radians. So the angular displacement of the rod after 3 seconds is about 2.25 radians. Now let's look at a second example. This time we're dealing with a wheel that slows down. We're told that the wheel has a radius of 0.2 meters and an angular velocity of 5.0 radians per second. It experiences an angular deceleration of 0.50 radians per second squared, and we're asked to find the angular velocity after one full rotation. Step 1 is to identify the known quantities. The initial angular speed is 5.0 radians per second. The angular acceleration is negative 0.5 radians per second squared. The negative sign here because the wheel is slowing down, so the angular acceleration is in the opposite direction to the initial angular velocity. Delta theta is given as one rotation, but we need to convert this to radians so that the units are consistent. To convert rotations to radians, we multiply by 2 pi, as this is the angular displacement of a full rotation. Next, we choose an equation that contains what we know and what we want to find. We're solving for omega f, so the most suitable equation is omega f squared equals omega I squared plus 2 alpha delta theta. Substituting the values into the equation, this becomes 25 minus 2 pi. Taking the square root, this comes out to be around 4.32 radians per second. So after one full rotation, the angular velocity of the wheel is around 4.3 radians per second. Let's now take a look at how rotational motion compares to linear motion when we graph different quantities against time. On the left is a displacement time graph for linear motion. The gradient of this graph represents velocity. When the acceleration is constant, the curve takes on a quadratic shape that becomes steadily steeper with time. As the quadratic steepens, the object is moving faster, showing that velocity is increasing. On the right is the equivalent angular displacement time graph. Here, the gradient represents angular velocity. When angular acceleration is constant, the curve is also quadratic, and it steepens in the same way. The steeper the quadratic, the faster the rotation. These particular curve shapes arise when acceleration, whether it's linear or angular, is uniform. Now let's compare velocity time graphs. On the left is a velocity time graph for linear motion. The gradient of this graph represents acceleration, while the area under the line gives the displacement. When the acceleration is constant, the graph is a straight line, showing that velocity increases at a steady rate. On the right is the angular version, where the vertical axis shows angular velocity. Once again, the gradient gives angular acceleration, and the area under the line represents angular displacement. A straight line here also indicates constant angular acceleration. Now let's compare the acceleration time graphs. On the left is the graph for linear motion. The area under the graph represents change in velocity. On the right is the angular version. Here, the area under the graph represents change in angular velocity. Now let's look at a final example involving a graph. Here we have a disk rotating with an initial angular velocity of 0.80 radians per second. The disk rotates for 5 seconds and we're asked to use the graph to find two things: the angular displacement of the disk and the linear acceleration of a point on the edge. First, let's calculate angular displacement. This is found from the area under the graph, because the area under an angular velocity time graph represents angular displacement. There are two parts to the area, a rectangle and a triangle. The rectangle here has an area of 0.8 times 5, and the triangle here has an area of 1/2 times 5 times 1.2. Altogether, this gives us a total angular displacement of the disk of 7 radians. Next, we need to find the linear acceleration of a point on the edge. Angular acceleration is the gradient of an angular velocity time graph. The gradient is the change in angular velocity divided by the change in time. So that's 1.2 over 5, which comes out to be 0.24 radians per second squared. We can then find the linear acceleration using the relationship a equals alpha r. Here the radius is 0.1 meters, so this gives us a linear acceleration of 0.024 meters per second squared. To summarize, these are the main equations that we use for uniform angular acceleration. They're just like the linear motion equations, but with angular quantities instead of linear ones. They show how the quantities of angular displacement, angular velocity, angular acceleration, and time are linked when angular acceleration is constant. These equations here connect rotational motion and linear motion. Displacement, velocity, and acceleration all depend on the radius, so points further from the centre move faster and have greater linear acceleration. The graphs are also analogous to linear motion graphs. For the angular displacement time graph, the gradient gives angular velocity. For the angular velocity time graph, the gradient gives angular acceleration, and the area under the graph gives that angular displacement. For the angular acceleration time graph, the area under the line gives the change in angular velocity. Finally, when solving problems, always start by listing what you know and identifying the unknown variable. Then select the correct equation and rearrange for the unknown variable. Check your units and substitute values into the equation. This approach works for any rotational motion question with uniform angular acceleration.